In this video, we're going to discuss what occurs to the vapor pressure when there's a mixture that has a dissolved, non-volatile material. What do I mean by that? Well, if you got your liquid and it's got various molecules of your water or ethanol or whatever else, but you also have something dissolved in with it, like say you have water and sodium chloride. We'll compare this to just pure water. So we'll have a closed container. We have our graph of energy distribution. Now remember that the energy distribution is for all the things. When you're at a temperature, all your material is vibrating and moving with an average kinetic energy for the bulk. Some are a little faster and higher energy, some are a little slower and lower energy, but the idea is there's a distribution, and that applies to all of the particles. So some of your water particles are low, some are medium, some are high, but it also means if you have salt, some of your salt is low, some of your salt is medium, some of your salt is high. And while these individual particles will jump back and forth as they bounce into each other, as long as you've got a lot of them, you can presume that they are fairly evenly distributed. Well, the idea for vaporization is that there's some energy for vaporization. That means there is some number of particles past that energy. That's energy vaporization for water. Any particle that isn't water, well, means water doesn't escape. In a pure water environment, every particle that has that energy and is at the surface and headed the right direction will be a water molecule that breaks free into the gas phase. In your mixture, some of the time that's the case, but every once in a while, it's going to be one of your sodiums or your chlorides that's at the surface that gets hit by everything else, tries to break free, but the sodium isn't water. It doesn't succeed. To knock the sodium ion free actually requires way more energy. This just means that one of the attempts to leave failed to make water leave. By having things in solution, you reduce the number of leaving events that put your water molecules into the gas phase. So while a pure liquid would have so many per second leaving, a mixture will have less per second leaving. Well, as you get things into the gas phase, you start building up a little bit of return rate and a little bit of return rate until you reach your vapor pressure, till equilibrium is achieved. However, you don't need as much in the gas phase before you cancel out the lesser leave rate of your mixture. The net result is that at the same temperature, a mixture has a lower vapor pressure than the pure liquid. The other things in solution simply inhibit water from escaping, or whatever your solvent is, and therefore less of them will escape per second. You need less pressure in the gas phase before the return rate's the same. Your vapor pressure that you will reach at equilibrium will be less. How much less? Well, for that, we can say that the pressure of our mixture, well, that's going to equal the pure pressure, the pure vapor pressure, times the mole fraction of the solvent. So X is mole fraction. X equals moles of your chemical over total moles. Since this is just an interference of a particle taking up the energy and not leaving, it's about the numbers. If 10% of your particles at the surface that have the energy to leave are not water, then 10% of what could have been water leaving doesn't occur. And so we need to know those total moles. Let's do an example here. I have 100 grams of water, and we'll make it something easy. I have 18 grams of sugar. So instead of salt, let's just look at a sugar molecule. I combine these, and we are at 90 degrees Celsius. Let's find our vapor pressure. In a previous video, we identified the vapor pressure at 90 degrees Celsius by calculating out using the Clausius-Capron equation. Well, in this case, we can take what it would have been if it was pure, and we can find what it will really be now in our mixture. If we go back to that value we calculated, we found it was about 503, but let's go ahead and just pull it from the table this time. Let's run for a slightly more accurate value since we're not calculating from two different temps. 526 torr. So the pure for water at 90 degrees Celsius, 526 torr. So I've got one part. I need my mole fraction. For that, I need to convert some weights to moles. Well, 100 grams of water, and that is 18.016 grams in 1 mole, will give us 5.55 mole of water. Sugar is 180 grams per mole, standard glucose here. We'll run with that. And so 18 grams, it's 180 grams in 1 mole, so 0.1 mole of sugar. Well, these are all combined together, so that makes 5.55 from water and the 0.1 from the sugar for 5.65 total. So what is the mole fraction of water, the solvent? Well, that's going to be 5.55 divided by 5.65. Water makes up 98.23%, or 0.9823 in fraction form. It's mostly water still. 18 grams of sugar, despite weight-wise being almost a sixth of the whole mixture, is a very small number of the particles. Sugars are large. They're 6 carbons, 12 hydrogens, and 6 oxygens all in a single molecule. And so it didn't significantly change the fraction that was water, but 1.8% indeed has been lost, and so we'll lose 1.8% of our vapor pressure. When we plug this in, what we will find is that the real vapor pressure of the mixture is going to be 526 torr times 0.9823. So the pure vapor pressure of the water times the mole fraction that is still water. So what vapor pressure would have been if it was 100% adjusted for our real percentage? We find is that it should be 517 torr. So it is reduced a little bit. Well, this can be more significant, especially if you have salt and the like in the ocean. Ocean water has a very different vapor pressure than fresh water. This affects our weather predictions and whatnot, as different amounts of water will rise into the atmosphere from different locations. Additionally, if you have an ocean near an estuary, it's going to be a different salinity than out over the deep ocean. So this also affects weather patterns in different regions based on the water output. The time of year, how much glacial melt there is will affect it as well. If we want to do the same thing but with 18 grams of NaCl in 100 grams of water, well, 18 grams of sodium chloride, but it's only 58.44 grams in 1 mole, which would be 0.30801 mole of sodium chloride. However, aqueous sodium chloride doesn't float away as pairs. When you dissolve an ionic substance, it tries to break apart completely into its separate ions. Which means instead of 0.3 moles of sodium chloride, it's really 0.3 moles of sodiums and 0.3 moles of chlorides. If they separate, they are different particles. Either of them could be at the surface. Either of them could take up a spot where water tries to evaporate. As a result, that means that our actual number of particles from our sodium chloride is between 0.308 all the way to twice that, 0.616. Not every ion pair successfully dissociates. Some of them really will be stuck together and others will break apart. This makes precisely calculating a ionic solvent's effect on the vapor pressure a little bit more tricky. Generally, as long as we're reasonably dilute, we'll run the assumption that it fully dissociates. We can calculate out what it really did based on vapor pressure later. So for our purposes here, we're going to assume it truly dissociated, that it went full ×2, broke those sodiums and chlorides apart. And that means we have 0.616 mole of ions. Well, we calculated out the moles of water before, so 5.55 mole from the water plus 0.616 mole of ions will give us a total moles of 6.166 mole total. That means the mole fraction that is water this time in this mixture is going to be 5.55 mole of water over 6.166 mole total, which is only 90%. So if I want to calculate the pressure of the vapor pressure in this mixture, well, it's still going to be the 526 torr if it was pure water, but this time times 0.9 instead of 0.98, which means the pressure of my mix is 473 torr. That's a rather significant difference, despite having the same weight of something dissolved in my water. Because of how many particles that represents, it actually affects our vapor pressure differently. And so we have to be careful of the moles. We need these mole fractions in order to calculate out these alterations to vapor pressure. So what vapor pressure our solvent will actually exert is dependent on what it would have been if it was pure, adjusted for what fraction of it is actually part of the mixture anymore. Now this works very well when we have a non-volatile thing dissolved. In our next video, we'll explore what happens when we have two volatile liquids mixed. As they both interfere with each other's vapor pressure, but they each have their own vapor pressure, how does that affect our total pressure?